Okay, so today we're going to go over the radius of convergence and the interval of convergence for a power series. Okay, so we're going to look at a power series that's centered at, well, it depends. Sometimes we say C. In this particular case, the notation is indicating that the center would be A. That's my sign. So if a power series is centered at A, there are three possibilities. I'm going to go backwards. Okay, so the bottom one, that your series converges only at the center. Okay, everywhere else it diverges. And what that means is that your radius of convergence would be 0. There is no interval of convergence. It's just going to converge at that one place, and that's the center. Okay, so no real stretch of imagination there. Let's go somewhere else. Let's talk about the next one. So we're moving up to number 2. So the series converges for every x. So the radius of convergence is infinity. So what that means is that the series converges for all x. That's like saying everything's going to work, so the interval of convergence would also be infinity. The set of all values of x for which your power series converges is your interval of convergence. Okay, so here's your center. Let's now talk about number 1. Okay, so number 1, there's a positive number r such that the series diverges for the absolute value of x minus a is greater than r, okay, but converges for the absolute value of x minus a is less than r. The series may or may not converge at either of the endpoints, x equals a minus r and x equals a plus r. So let's kind of talk about r here. So r would be your radius of convergence. So that's why before we were talking about maybe a unit circle or a different type of circle, because r, even though it's capital here, is kind of acting like its radius. And it is called the radius of convergence. So let's talk about your infinite geometric power series. So we know that the interval of convergence is between -1 and 1. And sometimes we have to solve for a new interval of convergence if it's for a function. So we take r, and we put it in between, and we solve, and maybe it's like -2 is less than x is less than 1. So it's just a good for instance, so you can actually see that in that particular interval that we have here, the capital R, radius of convergence is is 1. The capital R is 1 because every time you find your radius of convergence, if you know where the ends are and it's 2 units, you just divide by 2. So you may have heard me in another video briefly say, okay, the radius of convergence is half of the length of the interval. And that's why that actually works out, okay? So this is basically trying to describe the endpoints. So the endpoints, instead of using -1 and 1, may be different. And so we're going to label it, okay, as a minus r over here and a plus r over there, okay? And by the way, this is the center. We said the center was A before, so I should correct that. So now you kind of see the endpoints. And if you were to find the length, you would have 2r, you divide by 2, you get 1, so, or 1r. So it kind of makes sense with what I was explaining before, but these are the endpoints, okay? And so it makes sense that it converges for this just as much as was describing before with the infinite geometric series. Okay? Now, it's just referring to its power series. And divergence would be if it's greater than R. Now, if it equals R, it's a different story. But I think you get a good idea as to what's going on with this kind of diagram and story and background to what you guys copied. Okay, so we have an example here. Find the radius of convergence and interval of convergence of the series. Please copy this down. The sum of the rational function expression negative 2 to the nth power times x to the nth power over the square root of n plus 3. And we're finding the sum from when n is equal to 0 to infinity. So we definitely have an infinite power series here. Okay? We could see the x, we could see the infinity, we got an infinite series. So now let's take a look at a sub n. So this expression right here is a sub n, and we're going to take a look at using the ratio test. In the ratio test, we're going to take the limit of a sub n plus 1 and put it over a sub n. So as you're looking at this, hopefully it's a little bit of a review from our previous lessons on the ratio test. And you're probably wondering, why are we doing this? Well, the ratio test is how we're going to find our capital R, our radius of convergence. And we're going to then find our interval of convergence. So let's just make sure we write this correctly and can squeeze it in. I think we got it. Okay. That's supposed to be 3. Hopefully we got it down. All right. So let's try to rewrite this a little bit. All right, so in trying to simplify our complex fraction, we're ending up with this expression here. Up the bottom is done. There we go. Okay, so hopefully you got that down. If you didn't, please make sure you pause and make sure you got your example down. So we're going to start simplifying, making this a little bit easier to work with. Okay, so same base, you can subtract the exponents, and we're just going to get a negative 2 to the first power. And we're going to get an x to the first power. Okay, and well, we're not going to be able to do much simplifying of the square roots. We could leave that. Oh, and I put in parentheses. So does it make sense that it's going to be positive? Well, not really. We need to make sure that these are still absolute values. Okay, because x is in there still. And it says n approaches infinity. It's as, you know, it gets larger and larger. And here we know it's positive. But for x, we don't know. So we have to keep the absolute values. Okay, so if you look at this, we do have that negative 2 in there. And so we can say the limit of 2 times the rest of this expression. Now, if you are to keep this separated, okay, it's different absolute values. Let's think of our properties for limits. Well, the constant can be pulled out in front, and we also can take the limit of this factor, and the limit of this is going to be 1. You got n to the 1/2 power over n to the 1/2 power. So if that's true, we end up getting 2 times the limit, okay, of 1 times absolute value of x as n approaches infinity. So let me tell you something. N is approaching infinity. So x right now, even though it can change, we know it's a variable, but because n is the one that we would change and may go to infinity for this limit, okay, we're treating the absolute value of x as if it is a constant, okay? I don't know what it is, but we're going to treat it as such. So if we had like the limit of 5 here as n approaches infinity, we would just say it's 5. And you're going to treat the absolute value of x the same way. So what we have here is the ratio test. And the ratio test, okay, converges if this expression is less than 1. Okay? So when we go to solve for this, and I need some space, I'm going to have to erase this part. It's right underneath anyway. It's the part I said for you guys to copy. So if we set this less than 1, we find the absolute value of x has to be less than 1/2. Okay, so we find out that this is what's going to happen in order for the series to converge. So its radius of convergence is going to be 1/2. Okay, now we did all of that and all we got was the radius of convergence. So we do still have to find the interval of convergence. Okay, so let's figure out what we're looking at right here, and let's see if we can find out the interval of convergence. Okay, so let's erase some of this because we're done with that. We're just going to use, whoop, I don't need that. Okay, so we're going to use this inequality right here. This looks very similar to what we were using for an infinite geometric series. Okay, the absolute value of r is less than 1. Well, we got the absolute value of x is less than 1/2. So that means that x has to be between -1/2 and 1/2. But does it include the -1/2 or 1/2, or does it not? So that's what they were saying before about the endpoints. You must test for the endpoints of this interval. Okay? So what we're going to do is check when x is -1/2 and when x is 1/2 in your series. So how crazy is that? We actually end up needing some space, so let me keep erasing this. Hold on. We end up needing a substitution. Okay, so where are we going to substitute? We're going to substitute it into a series. So if we take a look at this series, okay, where x is -1/2, that's a plus. We have to see if this converges or diverges. Okay, and similarly, we're going to plug in +1/2 and see if this converges or diverges. All right. So let's take a look at what we have in our series. Okay. So first thing we're going to do is look at your numerator. Okay, they both to the nth power. I can multiply -2 with a -1/2. That's going to be 1 to the n. So no matter what n is, my numerator is just going to be 1. And we have this expression here. And we can use this as a p-series if you need to do a direct comparison test. Okay, you would still need to figure out that p is 1/2 for 1 over n to the 1/2 power, and that 1/2 is going to make this diverge. Okay, and if you continue to do the limit comparison test, then we also find out that this too diverges. So we're not going to include the -1/2 in our interval of convergence. Okay, so now let's figure out what's going on over here when x was 1/2. So we have the same exponent, we can combine the bases by multiplication. So we have -1 to the nth power. So we have an alternating series. Okay. And with an alternate series test, we need to say, okay, a sub n is 1 over square root of n plus 3, similar to what we had before. Okay, but it's alternating. So let's see what's happening here. Is the limit of this as n approaches infinity equal to 0. So if you use n behavior model, it is equal to 0. So if we continue, okay, and we compare our n plus 1 term with our nth term, and I ran out of space, so I'm going to have to bring it up here. So our n plus 1th term, what happened here? That doesn't look anything like the denominator. I'm having a problem with my marker here. Okay, n plus 1 plus 3. And our nth term, where's the plus sign? And we go to solve this inequality. That's a less than or equal to. Okay, square both sides. This makes sense. It is going to be less than. Okay. Subtract n on both sides. 3 is less than or equal to 4. So you know what? By the alternating series test, okay, this was convergent. So let's come back down. This is convergent. Converges. So if that one converges, that's very interesting. So that means that we can include the 1/2. So this is this interval of convergence. And we're done. So hopefully you had a good time going through that, finding the radius of convergence and interval of convergence. Just as a side note, if you did measure from -1/2 to 1/2, you get 1, you divide by 2, you get 1/2. So once again, you want to double check that your radius of convergence was 1/2. It was. So hopefully everything's good, it makes sense. And have a great time doing these. Bye.